Neutron stars and pulsars are currently a prominent research topic. They're one of the universe's strangest objects. Neutron stars play a pivotal significance in the universe. A recent study reveals that neutron star collisions are one of the primary producers of heavy metals such as gold and uranium in the cosmos. Welcome to another video of Cosmos Observer, the only destination for your space curiosities. After a Type II supernova explosion, all that's left is a neutron star, or, even stranger, a black hole. When a huge star dies, its fuel runs out, collapses under its weight, and explodes as a supernova. These stellar deaths can produce neutron stars, which pack more mass than our Sun into a sphere about the size of Manhattan. The core, the most central part of the star, collapses, compressing every proton and electron into a neutron. If the collapsing star's core mass is between 1 and 3 solar masses, the newly generated neutrons can prevent the collapse and leave a neutron star behind. Since neutron stars started out as stars, they can be found all around the galaxy in the same places that we can see stars. They can be discovered alone or in binary systems with a companion, just like stars. A teaspoon of neutron star material weighs 10 million tons. On Earth, one sugar cube of neutron star material would weigh about 1 trillion kilograms, roughly the weight of a mountain. Many neutron stars are likely undetected because they release insufficient radiation. They can, however, be seen under specific situations. A few neutron stars have been discovered at the cores of supernova remnants, silently emitting X-rays. However, neutron stars are more commonly encountered spinning furiously with high magnetic fields such as pulsars or magnetars. Pulsars were first detected around 50 years ago. The discovery of pulsars dates back to 1967 and provided evidence of the existence of neutron stars. It was found out by Jocelyn Bell and her advisor, Anthony Hewish. The majority of neutron stars are seen as pulsars. Pulsars are revolving neutron stars that emit radiation pulses at fairly regular intervals, ranging from milliseconds to seconds. Pulsars have extremely powerful magnetic fields that channel jets of particles out along their two magnetic poles. These accelerated particles produce extremely intense light beams. A lighthouse is the simplest way to explain a pulse. A lighthouse emits a beam of light that sweeps over the sky at night. The beam is only visible when it is unwaveringly focused on you, even though the light is always on. You see a pulse of light every time the beam points in your direction. Similarly, radiation from a small spot on a neutron star sweeps through space, giving us a pulse of radiation every time the beam points toward Earth. A pulsar pulses when the angle of view shifts midway through, allowing us to see light beams moving across our line of sight. Some particles follow the magnetic field and collide with the opposing side, heating the surface and forming hot spots at the magnetic poles. The entire pulsar glows slightly in X-rays, but the hot areas are more visible. As the item spins, these spots sweep in and out of view like lighthouse beams, causing extraordinarily regular fluctuations in the X-ray brightness. Even though the parent star rotated slowly in the main sequence, its rotation had to accelerate when it collapsed to produce a neutron star. Remember the conservation of angular momentum principle. It is a physical property of a spinning system such that its spin remains constant unless it is acted upon by an external torque. Put another way, the speed of rotation is constant as long as net torque is zero. When an item shrinks, it can spin faster. A neutron star with a diameter of 10 to 20 kilometers can complete one full spin in a fraction of a second. This is the type of time interval observed between pulsar pulses. Magnetar. A magnetar is another form of the neutron star. The magnetic field of a normal neutron star is billions of times that of the Earth's. However, the magnetic field of a magnetar is 1,000 times stronger. The magnetic field and the star's crust are bound together in all neutron stars, so any change in one affects the other. The crust is under tremendous strain, and any minor movement can cause an explosion. However, current nicer investigations of J0030 demonstrate that pulsars are not so simple. The NICER, Neutron Star Interior Composition Explorer, is a space-based X-ray telescope. Researchers use NICER to analyze the pulsar, which is approximately 1,100 light-years distant in the constellation Pisces. Two teams, one led by academics at the University of Amsterdam and the others by researchers at the University of Maryland, used X-ray photos from J0030 to map the pulsar's surface and determine its mass over time. NICER discovered that the forms and positions of million-degree hotspots on the pulsar's surface are far odd than previously anticipated while analyzing the pulsar's heft and proportions. Pulsars, like black holes, are incredibly dense but tiny objects. Their massive gravity bends space-time around them, allowing us to see the pulsar's far side even as it rotates out of view. The effect also causes the pulsar to appear slightly larger than it is. because NICER can precisely time the arrival of X-rays from the pulsar. The astronomers were able to create an unparalleled map of the star's surface and measure its size. Using NICER data from July 2017 to December 2018, two groups of scientists used independent methodologies to map J0030's hotspots and came up with identical estimates for their mass and size. The pulsar is around 1.3 times the mass of the Sun and 15.8 miles across. According to a team led by Thomas Riley and Anna Watts at the University of Amsterdam. Cole Miller at the University of Maryland, who led the second team, discovered that J0030 is roughly 1.4 times the mass of the Sun and somewhat larger, measuring approximately 16.2 miles in diameter. Since space-time is so twisted, light from the pulsar side facing away from us is bent and misdirected towards our perception. This causes the star to appear larger than it is. Because the hot patches rotate to the star's far side, they may never completely disappear. For the first time, scientists may benefit from this influence since NICER measures the arrival of each X-ray from a pulsar to better than 100 nanoseconds, which is 20 times greater than previously achievable accuracy. With less than 10% uncertainty, NICER's unmatched X-ray data allowed us to make the most exact and dependable calculations from a pulsar's magnitude to date. From Earth, we can see J0030's northern hemisphere. Based on the textbook image of pulsars, the teams expected to find one when they mapped the shapes and locations of J0030's dots, but they didn't. Instead, the researchers discovered up to 3 hotspots, all of which are located in the southern hemisphere. Riley and his colleagues recreated the X-ray signals by running rounds of simulations with overlapping circles of varying sizes and temperatures. Their investigation took less than a month on the Dutch national supercomputer Cartesius, but would have taken about 10 years on a current desktop computer. Their solution pinpoints 2 hotspots, one small and circular and one long and crescent-shaped. Miller's team ran identical simulations on UMD's Deep Thought 2 supercomputer, but with ovals of varying sizes and temperatures. They discovered 2 equally likely spot arrangements. One has 2 ovals that closely resemble the pattern discovered by Riley's team. The second option introduces a third, colder area that is somewhat off-center from the pulsar's south spinning pole. Previous theoretical predictions suggested that the positions and forms of hotspots could vary, but the J0030 investigations are the first to map these surface features. Scientists are still attempting to figure out why J0030 spots are grouped and formed the way they are, but it's evident that pulsar magnetic fields are more intricate than the standard 2-pole concept. The major scientific purpose of NICER is to calculate the masses and diameters of multiple pulsars with precision. Scientists will be able to finally comprehend the state of matter at the cores of neutron stars, substances crushed by enormous pressures and densities that cannot be replicated on Earth with this information. Astronomers have calculated that one new pulsar is born every 25 to 100 years somewhere in the galaxy, at almost the same rate as supernovae. According to calculations, a pulsar's usual lifetime is roughly 10 million years. Beyond that, the neutron star's rotation is too slow to create substantial beams of particles and energy, and it is no longer visible. We believe that our galaxy contains roughly 100 million neutron stars, the majority of which rotates too slowly for us to see.